Here I have a nice Calculus 1 problem for the channel, and it asks us to find the dimensions of the largest rectangle which has two corners or vertices that lie on the x-axis and two corners or vertices that lie on the curve y equals 12 minus x squared. Before we get into the problem, I just want to apologize for the lack of uploads recently. I was graduating and now I moved home. As you can see, this chalkboard layout is a bit different, so I had to move everything home and set this up, so I apologize for that, but the regular uploads should resume. Okay, so let's jump into the problem. First, I want to draw out our coordinate axis, and I also want to add in the curve 12 minus x squared. So we'll say this point right here is 12 on the y-axis, and from there we'll have our downward sloping 12 minus x squared, like so. So somewhere on this curve we'll have these points that make a rectangle, and we want to maximize this yellow rectangle. That's our goal here. So first I want to give these rectangles side lengths. We'll call it L and W for length and width. And we'll call that the area of the yellow rectangle. That's pretty self-explanatory. And we'll call the Y component, or the vertical component of this rectangle, L, and the horizontal component W. So I'll go ahead and denote that up here. Okay, but now what we want to do is solve for either L or W in terms of the other variable, and then plug it into this area equation, and then take the derivative and set it equal to 0, like we would in any other optimization problem. So we'll go ahead and solve for either L or W over here, but first we want to notice that L and W correspond to X and Y here in this equation, because L is the vertical component of this purple graph here, and W is 1/2 of the horizontal component, or I should say twice the component of the horizontal. If the X value of this vertice here is -2, then W is equal to the absolute value of 2 times that X component. So that would be 4 in this case, because we'd have -2 on this side and 2 on this side. Okay, so let's go ahead and write that down. We'll have L is equal to 12 minus W over 2 squared. And like I said, this is W over 2 because this W is twice the length of what our X component would be. But now because we have this parameter, we can plug this in to our area parameter over here and solve it for W. So we'll have 12 minus W squared over 4 all times W is equal to the area. But that means 12W minus W cubed over 4 is equal to the area. But now we want to take the derivative of the area, so we'll try to find dA dW here, or the derivative of area with respect to the width. And so that's going to be 12 minus 3/4 W squared. That's the derivative of this second term here. And so now we have 12 minus 3/4 W squared, and we want to set that equal to 0, which finds a critical point of this optimization problem. This will either give us the minimum or the maximum area, hopefully. Okay, so now we need to solve this for W. I'll go ahead and do that in this yellow box up here. So we'll have 12 minus 3/4 W squared is equal to 0. Now we move this right term across. We'll have 12 equals 3/4 W squared. And then multiplying by 4/3, we get 16 equals W squared, or W equals 4. We choose the positive square root here because negative values don't make a whole lot of sense when we're talking about area. But now if we plug this W value back into this equation, we'll find that the length is equal to 12 minus 4 over 2 all squared. But now we have length is equal to 12 minus 2 squared, which is 4, or the length is equal to 8. So we know that the maximum area occurs at length 8 and width 4. So that's going to be 8 times 4. And so we know that our maximum area here is indeed 32, because our endpoints would be when the area is equal to 0, because if we shorten this rectangle to be completely flat, that's an area of 0, and when we narrow this rectangle in on the x-axis, that's also 0. So our maximum area here is 32, and that's enough for now.